Welcome to this first chapter of this wireless fundamental course. In this chapter, we will talk about some standard organizations in the Wi-Fi world. We'll also cover some concepts of radio frequency, some characteristics, some principles of radio frequency. And to wrap the video up, we'll talk about some critical concepts of SNR, RSSI values, noise floor, fade margin. These concepts will form a strong base for us for the future videos. Okay, so cool. Let's get started. Uh, when we talk about some standard organization, the first one that comes to mind is, of course, FCC, which is nothing but Federal Communications Commission. FCC regulates communications within the United States of America and also to and from the United States of America. Okay, so FCC is basically responsible for setting up some Wi-Fi rules which every vendor has to abide by if they want to transmit data on the radio signals in the United States of America. They set up rules around frequency, at what frequency you can send traffic. They also, let's note that down, around frequency. They also tell you at which bandwidth you can send the traffic. Okay. They also regulate what can be the maximum power at which you can send the traffic. They also tell you what can be the maximum EIRP. We'll talk about this in the future as well in some of the videos. They also tell you whether you can use it indoor or outdoor. Sorry, let me just fix that. Okay, whether the use can be done indoor, outdoor. They also cover and tell you whether you can use Wi-Fi in the unlicensed band and the licensed band. Licensed band is nothing but where you have to pay some extra money to the government and get a specific spectrum for yourself to send traffic. Of course, it is costly. You have to pay a lot of money to use that special licensed band for your organization. That is the tough part because it's not free of cost. Whereas unlicensed band, this is the licensed band. Unlicensed band is absolutely free of cost. Okay, unlicensed band is absolutely free of cost, and anybody can use it. So that's the advantage. It's free of cost. And the disadvantage is that unlicensed band is used by anybody and everybody in the Wi-Fi world. So if I have my APs transmitting on the unlicensed band, then I also have my neighbor's AP transmitting on the same band, right? Now that's a disadvantage, but everybody uses that because the licensed band is specifically designed for some special segments of the nation, like probably military. So they have some special bands which they use for their own transmissions, uh, and that's pretty much what is done by the FCC. Okay. Now, different countries have their own bodies which decide and set the rules of a Wi-Fi. India has something called WPC. We have Europe, which talks about all these rules, regulations which are set up by ETSI. So every country and every region has their own company or own body which regulates these rules, and every other vendor that has to transmit data on the Wi-Fi needs to abide by those rules. Otherwise, you've got to pay a lot of fine if you break those rules. Okay, that's FCC and other bodies for you. The next body that comes to my mind is Wi-Fi Alliance. Okay, now Wi-Fi Alliance is nothing but it tells you about the interoperability of WLAN products. Okay, now Wi-Fi Alliance is actually doing nothing but testing the ability of all the WLAN products and giving you certificates on that. Okay, now if I own a company and I bring up a Wi-Fi access point, and if I launch a Wi-Fi access point, it needs to go through a Wi-Fi Alliance certificate for it to be sure that yes, this AP or this access point can operate with other Wi-Fi products in the market, like an Apple phone or a Samsung smartphone or a laptop or any other product out there in the market. They follow some standards, some basic standards of IEEE, and they perform absolutely well and they abide by all the rules. That is something which is told to us by Wi-Fi Alliance. So what they do is they do some tests, and then at the end they give us a certificate like this, where Wi-Fi Alliance will be mentioned here, and out here at the top there'll be some certificate ID which will be given to you, and which will define what standards it follows and if it is if it's good to go or not. So usually it takes a lot of time for a company to acquire a Wi-Fi line certificate, because there's a whole big queue that you have to get in line and basically then apply for it. And also, it's not mandatory for every product to have this certification, but it's really really important. Okay, and the thing is that if you launch a product, you probably have to apply it once the product is launched, and then it takes some time for the certificate to come to you, right? Because of course there are a lot of vendors out there in the market that is applying at the same time. So you get in the queue and then you wait for your turn to get the certificate, right? So Wi-Fi line certificate does that for you, and it's of course quite critical for you to obtain that, because a lot of customers in the market, they look for that certificate for your product. So if you want to get a customer base or you want to sell your products, you got to make sure you have this Wi-Fi LAN certificate. Okay, so if you are new to this networking industry, you probably have heard about the terms like core, you know, distribution, and of course access, right? You've heard about these three terms. The core of the network is probably a high-speed backbone or a super highway for network, right? The core is responsible to carry large amount of information between key data centers. That's what the job of the core is, right? The distribution on the other hand is responsible for directing the traffic, routing the traffic between or towards the smaller clusters of nodes or neighborhood of the network, right? Whereas the access layer is responsible for making sure that the traffic is delivered to the end user, right, to the edge of the network, right? Now, Wi-Fi, if you understand, Wi-Fi is responsible for connecting the edge devices, giving connections to the users at the edge, which means a Wi-Fi access point always needs to go and connect to the access layer. Okay, where do we place the access point? Always on the edge switches. This is important because as somebody who deploys a Wi-Fi network, you need to know where to place the access points and why. Okay, now that is quite critical. It won't hurt us if we place it on the distribution, but access point should be placed on the access layer. Some next so let's move on to the next concept of what a signal is. Okay, in Wi-Fi, I'm sure you remember this from your school days, what is called a sine wave. A sine wave goes like this. Okay, think of it like this. This is a transmitter, and here we have a receiver. Now, the transmitter wants to send some data to the receiver. Okay, and it will go in this wave, which is called a signal. Now, we understand that data has to be sent in zeros and one. So whatever data we have to send, it has to be first converted to bits, zero and ones, and then it has to be sent from transmitter to the receiver through the signal. Now, how we adjust these bits onto the signal like this, it'll be like zeros and then ones, zeros, one, or one, and then zeros, whichever way it is. This is called encoding the data onto the signal. Okay, encoding the data. right? Now, how this encoding is done is called modulation. Okay, encoding, adjusting the bits onto the signal is called encoding. How that encoding is done is called modulation. Now, modulation can be of multiple types. It can be direct sequence spread spectrum. It could be OFDM, orthogonal frequency division multiplexing. It could be quadrature amplitude modulation, right? It can be even more. But how we do encoding is called modulation. And once modulation is done, the resultant signal that comes out is called a carrier signal. Now, this carrier signal is responsible for carrying data from the transmitter onto the receiver. Okay, I'll repeat this once again. Uh, the transmitter has to transmit data to the receiver. Data ultimately is only going in bits, zero and ones. Okay, now how we encode those bits onto the signal is called encoding, or I would say adjusting the bits onto the signal is called encoding. How we adjust these bits is called modulation. And once modulation happens, the resultant signal is called a carrier signal. Now, this carrier signal is responsible for carrying data from transmitter onto the receiver. Okay. Now, this is critical, and we're going to use this in the future videos as well. So, if you have not understood, then you can rewind and watch this once again. The next concept that we come to, basically, we're going to talk about some characteristics of radio waves. Okay. The first one that we talk about is amplitude. Now, what is an amplitude? If we have a signal like this, okay, amplitude is nothing but the height, the force, or the power of the signal. Okay, so this is called the amplitude of this particular signal. As simple as that. Okay, second is the wavelength. Uh, okay, let's correct that. The wavelength, also represented as lambda. Okay, this is just a symbol. You don't need to really go in depth as to why it is called lambda, but just a symbol and as to how we represent a wavelength. Let's say we have a signal like this. The distance between two similar points is called a wavelength, also represented as lambda. Okay. Similarly, this is also lambda, right? The third principle or the third characteristic is frequency, which is represented as hertz, hertz, Hz. Now, frequency is nothing but how many times a signal repeats itself in 1 second. That's the cycle of a signal. Okay. When we talk about 1 hertz, we say 1 cycle per second. When we talk about 1 kilohertz, we talk about 10 to the power of 3 cycles per second. When we talk about 1 megahertz, we say 1 into 10 to the power of 6 cycles per second. When we talk about 1 gigahertz, we say 1 into 10 to the power of 9 cycles per second. So when we say 2.4 gigahertz spectrum is in which we pass traffic, we are saying that in this frequency band, the signal repeats itself 2.4 into 10 to the power of 9 cycles per second. And 5 gigahertz, it is 5 into 10 to the power of 9 cycles per second. That's how many times a signal repeats itself in 1 second. That's the frequency of a signal. Okay. The next is of course the fourth characteristic, which is phase. Now, phase is nothing but a relative term, phase of a signal. When we talk about phase, we are always talking about two waves, not just one. So here it is. If I draw a wave like this, and the other wave is something like this. Okay. Now these waves are identical, but they are at a gap of 90 degrees. They have the same amplitude, they have the same wavelength, but they are 90 degrees out of phase. Okay. So the phase difference between these two waves is 90 degrees right now. And they are out of phase, of course. Okay. So that's the concept of phase, and which I mean these three four characteristics you need to know about a radio wave, because these concepts will be used in the future videos as well for you to really get more insights around how an AP or a client communicates, and what is multipath, how these things really come in handy for our multiple other concepts in the coming videos. The next thing that you need to know, we talked about radio waves, but what exactly is a radio wave? What is exactly is a radio frequency? Okay, so what is a radio frequency? So we have heard of an electromagnetic spectrum. Okay, what an electromagnetic spectrum is usually referred to as just spectrum, and it's a range of all electromagnetic radiation. Okay, so here is the electromagnetic spectrum, which consists of infrared, radio frequencies, ultraviolet rays, X-rays, gamma rays, visible to the naked eye, that's visible rays. So if this is visible light, this is X-rays, this is gamma rays, this is something like infrared, for example. This is microwaves or radio waves. Let's say this is radio waves. This is microwaves. So what we can see from our naked eye is the visible spectrum. Where we transmit Wi-Fi is called a radio wave spectrum. And this entire thing is an electromagnetic spectrum. So a part of electromagnetic spectrum which is used for transmission of radio waves is called a radio wave portion here. That's the portion we get to do wireless transmissions on. Okay, and of course this is something which defines what radio frequency is, and this is something which we should know. Uh, just a small portion of electromagnetic spectrum is what we get to transmit radio signals. Okay, cool. So that was the concept of radio frequency. We are also going to talk about some other concepts of, when I say concepts, I mean some RF behaviors now. Okay. RF behaviors kind of like how the RF can behave when it is propagating. And with the first word that comes to mind is wave propagation. Okay. Now, wave propagation is just the way a wave moves forward. Okay. When you drop, let's say you drop a pebble into the ocean, how does a wave initiate? It kind of initiates something like this, right? When you drop a pebble, a wave initiates like this. This is called the epicenter of the wave. Okay. And this is pretty much how the wave. So with the amount of power you drop the stone in the ocean, it depends on how far the wave will go. Okay. And there has to be one epicenter in the right at the center. So this is called wave propagation. This is how a wave propagates. Okay. Now that is just one principle. That is just one behavior of the wave. The second is, of course, what we say is absorption. Okay. For you to understand what absorption is, I want you to imagine that you're in a room, and let's say we have an access point deployed into a room, which is, let's say, this room, and the access point is here. Or let's say you are, forget about the access point. This is a transmitter and this is a receiver. Okay. Now, the transmitter is trying to send some data to the receiver, and there is a table right here, there is a ch chair right here, or there are some curtains right here onto the window, anything. So what I'm trying to say is, when a transmitter sends some data on to the receiver, there is a possibility that the RF signal might get absorbed by the surroundings. The signal goes from here, it hits here, and then some part of it goes here to the receiver. Something like this happens directly. It can go hit this wall, it can go hit this window, table, chair, or anything. So basically, the signal is absorbed by the obstacles that come in between the transmitter and the receiver. Let's say a dry wall will have some sort of an attenuation. Attenuation is nothing but loss. So absorption can cause a lot of loss as well. By the way, yeah, anyway, so what I was saying was that the transmitter is trying to send some data onto the receiver, which will hit a lot of obstacles in between, which will cause the loss of the radio signal. It can also be basically be responsible for other factors as well, which we're going to talk about in the next few minutes. A dry wall, let's say, has some attenuation. A brick wall has, let's say, something a higher attenuation. A cement wall is also responsible for a lot of attenuation. Dry wall has the least attenuation when it comes to walls. Brick wall and cement wall, they have more attenuation, so they absorb more signal and cause more attenuation, of course. And the third behavior of RF is called reflection. Now, reflection is nothing but, let's discuss with the example, transmitter and receiver. So I'm going to draw something, a similar diagram. When a transmitter wants to send traffic onto the receiver, a wave can take multiple paths, not just one. This wave can fall onto the walls, fall onto the plane surfaces, fall onto the glass, and can go to the receiver in different ways, in different directions. And of course, let's say this is wave number one, this is wave number two, this is wave number three. Reflection can happen mostly in the indoor environment, where you have in a classroom or in an office room, you have multiple places where reflection can happen. Now, wave number one, wave number two, wave number three will all reach the receiver at different times, right? There might be slight delay of milliseconds. That delay is called delay spread. Okay. That delay between these three waves is called delay spread. We will discuss more about this in multipath, where I'll explain the cause of reflection and how it can be beneficial, how it can be destructive to our RF signal. But that is the third kind of that is the third characteristics or behavior of a radio signal. There's something called refraction. Now, refraction is nothing but bending of RF signal. Okay. How this works is, let's say, whenever an RF signal passes from one medium to the other, which means it is passing from air to water, or it is passing from water to air, or it goes from air to water, then again out to air, there is a bending of RF signal there that is happening. For example, if you are standing in a swimming pool, okay, let's say this is air, your signal comes right here. Then when it moves to a different medium of different density, the radio signal will bend a bit. Instead of going straight, it will bend a bit, and then when it goes out, it again moves out like this. Okay. Now, due to this bending, refraction happens. If the device was somewhere here, it will think that the device is somewhere here. This is called refraction because of bending of the RF signal when it moves from one medium to the other. That's another characteristics or another behavior of the radio frequency that you should know, which will cause some loss or which will cause some attenuation of the RF signal. There are other behaviors as well, like scattering, like diffraction. We're anyway not going to go in details of that. But the common thing about all these behavior is that they're going to cause a lot of loss to the RF signal. Loss is also known as attenuation. Okay, we lose signals because of it, because of these characteristics or these behaviors of the RF wave, and this is quite essential for us to know, how things really work in practical life. Okay, one more behavior you should know is something called a free space path loss. Now, imagine yourself standing in an open field, in an open ground, and there is somebody who is 10 feet away from you. Okay, you call out his name with the X amount of power, he's going to hear it quite well. The guy moves 10 feet away, so now he's 20 feet away from you. You again call out his name with that X amount of power, he'll be able to hear you okay, okayish. And if he moves further away, then let's say he's now 50 feet away from you. You call out his name with that same amount of X amount of power. He may not be able to hear you now. Why? Because he moved quite away from you. Now, this is called free space path loss. Even though there is no absorption happening, there is no reflection happening, there is no refraction happening, or there is no scattering or diffraction happening, but still, due to free space, you can call it, beam divergence, you can call it air friction. The loss of the RF signal happens because of free space also. So that loss is called free space path loss. We have to also take into account this loss when we transmit and when we receive data from a transmitter and a receiver. Cool. So that these are the some characteristics about the wave propagation and some behaviors of it, which you should know, which will cause heavy loss in the practical world. The next concept is a bit detailed. I want you to know. Let's do this. Let's move to the new page altogether. Okay. We will discuss the concept of multipath now. Multipath is one of the major enemies of RF transmissions. Okay, or I should say it was. Now it's not. I'll discuss more on that though. But we need to understand the concept of multipath first. So multipath is basically is a propagation phenomena that results in two or more paths of a signal arriving at the receiving antenna. Okay, same diagram what we drew earlier, transmitter and receiver. if I need to send something from transmitter to receiver in an indoor environment, and I'm using an Omni antenna, which is again going to spread the data in the air in all directions, my traffic will reach like this. It can reach like this. It can reach like this. It can reach like this, or it can also reach like this. And there are multiple paths that the RF can follow to reach the receiver. So I see four waves which are getting received at the receiver of the same data. There will be some delay. The delay between the two waves is called delay spread, which we discussed earlier, is called delay spread. Now the cool thing is that these four waves are responsible for basically carrying out four different things. The results can be four folds. Okay, one is upfade. Let's say there are two waves reaching the receiver from the transmitter. One is of amplitude, let's say 1, and the other one is, let's say, amplitude this 0.5. Upfade is the resultant wave is a combination. The amplitude kind of increases, becomes more, which means now the amplitude is 1.5. The amplitude got added from the transmitter and the receiver. This is called upfade when the resultant wave is an addition of the two waves that we see. Second behavior is called downfade, okay, which means it has a negative impact on the amplitude. It's kind of, the resultant wave has lower amplitude than the first wave. So let's say this is the transmitter, this is the receiver. This has the amplitude 1. The second wave that arrives has an amplitude of 0.5, but in the opposite direction. Okay. The resultant wave becomes something like this with an amplitude of 0.5. Now this is downfade. The amplitude got reduced. The third, how it can behave another way is something called data nulling. Let's say this is again of amplitude 1 from the transmitter and going to the receiver, and the other wave that reaches the receiver has an amplitude of -1. Now the resultant that comes out is a straight line. There is no amplitude. The data got nulled. The data got cancelled. Okay. And the fourth behavior, which is the most common behavior, is data corruption. Okay. Data corruption. How it works is this is in fact the most common in because of multipath. So I have a transmitter and a receiver. Let's say I am receiving one signal like this, then I receive the other signal, some distorted signal like this. Then third one, I receive something like this. It can be various signals that I receive. That's why it's the most common. So the resultant signal that I get is something which the receiver cannot even comprehend. It's called data is corrupted. It could be something like this or completely distorted, which the receiver says, I cannot comprehend that. You need to send that to me once again. I didn't understand what you said. Okay. That's called that's called data corruption. So imagine yourself in a room, in a vacant room where you shout your name and then you hear echoes coming from all directions. That is called multipath. You are listening to your same signal from multiple directions. Okay. That's the practical example of multipath. So if you're transmitting anything in from the access point, you're trying to talk to a client from the AP, it is possible that multipath is happening even at that level. We were able to now, as we moved quite advanced in Wi-Fi, we have done a lot of advancements in Wi-Fi. We are able to now make sure that multipath can be always constructive for us. That was launched is always constructive for us. That technology is called multi-input, multiple output. It was launched in 802.11n. Before this, that is in 802.11 ABG, we'll discuss more about this though. Multipath was a real pain for RF transmissions. It was only after .11n when multipath could be used as always constructive. Okay, we're anyway going to discuss more when we go to .11n, but for now, these four behaviors is something which you should know, and multipath is one of the biggest enemies of RF transmissions. Cool. Okay, the next concept that you should know is called, so we talked about loss right now as to how loss can happen. We'll talk a bit about what gain is. Gain, also known as amplification. In simple terms, we are increasing the amplitude of the signal and we call it gain. Gain can be of two types. One is, of course, active gain. Another is called passive gain. Active gain happens when we supply an external power source to boost the signal. Okay. Passive gain, in passive gain, we are not supplying any external power source. We are just using the focusing ability of the antenna to increase the gain. Okay. Now, passive gain, so antennas are basically passive devices. We'll talk more about what an antenna is, but you should know that in active gain, we have to supply power from the external source. But in a passive gain, we are just focusing the antennas. We are just focusing the signals using the antennas, and hence we are increasing the gain. That's called amplification. Okay, cool. So moving on, what we can discuss now is something around the RF components and what they are, which is, when a transmitter wants to send some data to the receiver, what all components come in between is something that we should be aware of. How it happens really at the back end, how data is transmitted at the back end is something which we should know. So before that, we need to know what is a transmitter. Trans, what is a transmitter? Okay. Uh, so transmitter is responsible for, so when a computer hands the data off to the transmitter, it is the transmitter's job to begin the RF communication. So transmitter is responsible for beginning the RF communication. Okay. Now this is basically when data comes from the backend, it comes in the AC form, AC signal, alternating current signal. It needs to be converted to zero and ones, right? Correct. We'll move forward and talk more about that though. Next comes the antenna. Okay, so when connected to the transmitter, its job is to convert AC to RF, radio frequency, and transmit out in the pattern of the type of antenna that we have. Okay, so when connected to the transmitter, it collects the AC signal that it receives from the transmitter, and directs or radiates the RF wave from the antenna in a pattern specific to the antenna type. Let's say my antenna is omnidirectional or semi-directional or highly directional. It uses that pattern and directs the RF outside the transmitter. When connected to the receiver, it takes the RF signal and changes that into AC and sends out to the receiver. I'm sorry, I'll just correct that. Okay. The next thing that you should know is what is an intentional radiator. Uh, don't go into too much details, but an intentional radiator is the component that is responsible, specifically designed to generate the RF as opposed to something that generates the RF as a byproduct. This device is specifically designed to generate the RF signal. Okay, this is what generates the RF signal. When I make a diagram after this, it's going to make much more sense to you. And the next thing is EIRP. EIRP is nothing but equivalent isotropically radiated power. Think of it as the maximum RF signal strength that can be transmitted from an antenna. It is the maximum RF signal strength that can be transmitted out of an antenna. There are rules around EIRP when we talked about FCC and WPC and ETSI. They define what can be the maximum EIRP coming out of the AP or coming out of an antenna. They define those rules, and everybody has to stay in the limit. They cannot exceed. So if I designed if let's say in my country the rule is that no Wi-Fi product should be transmitting more than 25 dBm of EIRP, then if anybody is transmitting at 26, they have to pay a heavy fine, right? That is the maximum RF signal strength coming out of an access point is called the EIRP. It's the power at which the AP is transmitting plus the antenna gain. Okay, so yeah, that's called EIRP. Now, now how this all is stitched together is something like this. So we have something called a transmitter. The data is sent from here in AC. Okay, now transmitter is connected to an intentional radiator, which is connected to the antenna, and the radio signal goes out of it. This is the antenna cable. It is optional. It can be there, or the transmitter can directly connect to the antenna as well. Okay. Now, from here, the antenna EIRP is, is going out. Now, here at the receiver end, we have another antenna that connects to the EIR and goes all the way to the receiver through the antenna cable. Okay, here RF is received and sent all the way to the receiver. Data comes, hits the transmitter through the cable, goes to the IR, goes to the antenna. EIRP is calculated and sent out in the form of RF. Here RF is received and is converted to AC and sent to the receiver. Okay, antennas are responsible, again, as I said, antennas are responsible for converting AC to RF when connected to the transmitter, and when connected to the receivers, they are responsible for converting RF to AC and then sent all the way to the receiver. This is how it happens in a nutshell. Okay, so this is something, again, just for your knowledge. This is not something that you need to mug up. Just to give you an idea as to how it all connects, and how the transmission is happening at the back end. That's the reason why I just took a couple of minutes to draw this for you. Cool. So I also want to discuss a few more concepts before we close this video out. Okay. The first concept is what is called a noise floor. Okay. The noise floor is nothing but the background level of radio energy on a specific frequency. Think of it like the background noise or the background radio energy. I'll just write that down for you. Background radio energy on a specific frequency. Okay. Uh, so anything electromagnetic has the potential of raising the amplitude of the noise floor on a specific frequency. Whether it's, let's say, if you talk about 2.4 gigahertz, we say yes, on 2.4 gigahertz, we have baby monitors, we have Bluetooth, we have microwaves, or we have other APs which are transmitting on 2.4 also, other access points also. So for me, if I'm an AP, if I'm transmitting on 2.4, my neighboring APs can also raise my noise floor. When they are transmitting on their own signals on my frequency or on the same frequency, they can raise my noise floor also. Okay. It's like the background noise that is really causing me not to talk properly to you. So if I am talking to you in a room and we have other people around us who are also talking to each other, then you won't be able to comprehend me that well because you're also able to hear people around us talking, right? So that's what noise floor is. That's the reason why uh, the more the noise floor, the less likely that you'll be able to comprehend me. The other concept is signal to noise ratio. We also call it SNR, okay, which is nothing but signal minus noise in decibels. Okay, this is called SNR. Now, signal is what we receive from the transmitter. Noise is the noise floor around us, which gives us the value of SNR. So we have heard about SNR a lot, that SNR needs to be high for us to have better transmissions. Before I go in the detail and give an example, I want to talk about received signal strength indicator, which is also called as RSSI. Now, what is an RSSI value? Okay. To understand in detail as to what RSSI is, you have to understand the concept of received sensitivity. Received sensitivity is always at the receiver. Now, what it means is, what is the minimum value of signal I need to receive for me to be able to decode that properly and understand what you were trying to tell me? Okay. The power level at which I need to minimum receive the signal at for me to be able to comprehend you properly. That's called sensitivity. So if you are transmitting a signal at X amount of power and my receive sensitivity is, let's say, Y, then I need to be able to receive that at least Y so that I'm able to know what you really meant. That is my receive sensitivity. Okay. Signal strength is nothing but the strength of the signal that I receive as a receiver. Now, if this is a transmitter and this is a receiver, the transmitter is sending signals at whatever power. I'm receiving the signal, let's say this sent the signal at, let's say, minus 65. By the way, in RSSI value, received signal strength indicator, it can vary from 0 to minus 255. Okay. So since it's in negative, minus 60 is going to be better than minus 65, of course, since it is in the negative. So we say minus 60 dBm is better than minus 65 dBm. Is that correct? Yes, it is correct. Okay. If my transmitter is transmitting at minus 65 and my receiver is receiving at, let's say, minus 72, which is good enough for me to comprehend what the transmitter was trying to say, then I'll be able to decode the signal and convert that into zero and ones, and then basically make sense of the data that is coming towards me. If my received sensitivity is minus 70 dB, okay, and I receive this data at minus 72, which means now I am not at a, I won't be able to comprehend what was coming from the transmitter, because it is more than it is, I'm sorry, it is lesser than the value of my received sensitivity. If I can comprehend data till minus 70 dBm, and if I receive anything beyond that, that is minus 72, I won't be able to comprehend, and I'm going to make sure the transmitter retransmits that to me. Okay, that is called received sensitivity. That is the significance of received sensitivity in an RF transmission. Now, received signal strength indicator is the strength of the signal in simple language, which is denoted from 0 to minus 255. Now, moving forward, or I would say coming back to SNR, let's say my signal is minus 65 dBm that I hear, and my noise is minus 90 dBm. So SNR for me becomes signal minus noise, which is actually nothing but minus 65 minus 90 equal to minus 65 plus 90 equivalent to 25. So you must have heard SNR of SNR greater than 25 is considered very good. SNR somewhere around 20 is considered okay. SNR below 20, not good. There needs to be some work done to increase the SNR. We can get the quality of this wireless transmission better with a better SNR. So SNR is the difference between signal and noise, and it should be above 25 for good transmission in the Wi-Fi network. This is the standard value. Of course, it can go to 35, 40, whatever you, depending on how good the environment is. But yes, SNR depends only on signal and noise. Cool. Now, there is one more concept that you should know before we wrap the video up, which is called fade margin. Okay. Now, if my transmitter and receiver are here, and the received sensitivity of my receiver is, let's say, minus 72 dBm, which means if I hear a signal beyond minus 72 or minus 73, minus 74, then I cannot decode what the transmitter was trying to say. Okay. We all know that when the signal originates from the transmitter, there can be reflection happening, there can be absorption, scattering, refraction, which means there can be loss in the air, right? Now, if I send out a signal at minus 72, then it's possible that there will be some loss occurring in between here, and what I receive here at the receiver will be way beyond minus 72, will be somewhere around, let's say, minus 80 or minus 82 dBm, and I won't be able to comprehend. So we have to put some extra cushion at the transmitter end so that we are able to receive the signal at the receiver, which is more than the received sensitivity of the receiver. So I will not transmit the signal at minus 72. I will transmit the signal at least minus 62 or more, so that the receiver can receive the signal at minus 72 or below that, or let's say minus 70 or minus 69, for it to be able to comprehend that well. Now, this extra 10 dB of cushion that we took, 10 dBm of cushion that we took, this is called my fade margin. That I'm actually keeping a cushion so that my receiver is able to comprehend that well. So, guys, received sensitivity is at the receiver, fade margin is kept at the transmitter. Okay, this whole thing is to make sure that my receiver is able to comprehend whatever is coming from my transmitter and is able to make sense out of it, right? These are some concepts of radio frequency. These are some concepts of wave propagation which you should know, and these concepts will form a base for us for future videos, and to help us understand some very critical but very much needed concepts of RF waves. So thank you guys for this lesson. We're going to continue in the next chapter. And I hope you liked it, and I hope you learned something out of it. Thank you so much.